Hi everyone, my name is Harshad. I'm a software engineer at Google and my collaborators are Saurabh and Theodore. So Saurabh is a research engineer at Google and Ted, who is also ext4 maintainer, is one of the colleagues. So today I'm going to talk about our work on FastCommits, efficient file system journaling. This is how my talk is going to look like. So let's get started with background and motivation. So updating file systems to reflect changes made to files or directories usually requires multiple separate write requests. This makes it possible for interruptions like power failures or system crash to leave file system data structures in an inconsistent state. That can lead to data loss. So journaling is a popular technique that is used by many file systems to prevent against such crashes. What happens in journaling is that an area of the file system is reserved as a journal. Before updating blocks into their final locations on the disk, they are first written to the journal. This operation is called journal commit. Users can also trigger this journal commit via a system call called fsync. In case of a crash, failed blocks can simply be then recovered from the journal and file system returns back to consistent state. Since journaling sits right in the middle of the write operation path, its performance is very critical, and the overall file system write performance heavily depends on journaling performance. There are two main types of journaling: physical journaling and logical journaling. What we saw in the previous slide was physical journaling, where you write the entire copies of metadata blocks to the journal. In logical journal, instead of writing changed blocks, you write the operation that is being undergoing to the journal. So logical journals typically just write a few bytes on fsync, but physical journal ends up writing more blocks. Recovery with physical journals is simple because you just copy back the blocks. There are less chances for errors and stuff. But logical journal actually needs to replay the exact same data structures back onto the file system, which is why replay with logical journals is a bit complicated. So ext4, which is the default file system in many Linux distributions such as Debian, Ubuntu, is one of the most widely used file systems today. JBD2, it uses journaling by JBD2. JBD2 stands for Journaling Block Device, which is a journaling subsystem in the Linux kernel. It's a physical journal. Now let's consider this simple program, which is creating a file, writing 4K bytes to it, and then calling fsync on it. It looks like a simple program and it's not doing much, so you would expect that fsync call actually doesn't do much and should just return pretty fast, but that's not what happens. So let's look at what ext4 actually writes on disk when fsync is called. It first starts with a commit descriptor block. This marks the beginning of a journal commit. It then writes all the changed metadata blocks. In this case, creation of inode led to changing of inode table, inode bitmap. Allocation of block for write request led to block bitmap changes, and group descriptor, which contains a summary of free blocks and free inodes, that also got changed. It then issues a cache flush to ensure that all these changed blocks are persisted durably on disk. And to conclude the commit, it writes a commit marker block. And these operations happen via two serial IO requests. So on fsync, basically there is IO request 1 flush IO request 2. So that can lead to fsync being the performance bottleneck. Things become much worse if the frequency at which fsync is called actually increases. So in this example, to see this effect, what we do is we took the same program, which is creating a file and writing 4KB blocks. But now instead of calling fsync once, we call fsync at different intervals, starting from fsync after every file versus fsync once the entire run. And this is how the overall journal overhead looks like. So as you can see, on the x-axis we have fsync interval, that is a duration, number of operations between fsyncs. As fsync becomes more and more frequent, the data that gets written to journal increases exponentially, whereas user data kind of stays the same. So higher fsync frequency using JBD2 journaling not only results in reduced application throughput, but also results in higher journaling overheads, which can result in greater journal interference. That can leave fewer disk resources available for actual user workload. Given this, you would expect that fsync in real world workloads is not called that often, but many popular workloads in fact do end up doing fsync frequently to meet consistency guarantees. NFS, for example, issues implicit fsync call on every file system metadata update. So even if you just create a file, you don't call fsync, NFS is going to issue fsync right after that. Databases issue fsync on transaction log writes. Mobile applications are known to issue fsync at very high frequency. Mail server is another workload where we see high fsync frequency. And this graph shows the amount of bandwidth consumed by journal versus the user data. As you can see, journal consumes 4x the user data bandwidth. When this exact setup runs on cloud-based environments, these inefficiencies translate to direct dollar costs. That's because cloud environments allow you to provision the IOPS and bandwidth of the disk. So to take journaling into account, users need to provision more throughput and IOPS on the cloud-based block devices. That can lead to increased costs. So to minimize all of these inefficiencies and improve the end application performance, we present fast commits. So fast commits minimizes journaling overheads, it improves fsync latency, and that in turn improves the end application performance. So in the same mail server workload, fast commits consumed 44% lower throughput, lower disk bandwidth, and even then the application was, the workload finished 33% in 33% lower time. So fast commits is a hybrid approach to journaling, where it performs logical journaling on fsync and periodic physical journaling. So fast commits has been designed with the goal of industry use, and we make many careful considerations about the end user expectations, backward forward compatibility, and so on. Details about this can be found in our paper. Fast commits has been merged in the upstream kernel and it is available for everyone to use. There is like, so 90% of the code is merged upstream and 10% code is being reviewed right now. So the closest related work in this area is iJournaling and CJFS. iJournaling was in fact the first one to introduce hybrid journaling approach, and fast commits design is loosely based on iJournaling. However, iJournaling does not optimize for resource efficiency. We see that under high fsync frequency, iJournaling could end up writing more blocks to journal than ext4. Also, iJournaling changes the consistency guarantees of fsync on ext4. That would break existing users if they were migrate to using it. CJFS is the state-of-the-art JBD2 optimization that improves JBD2 scalability. In our evaluation, we compare against CJFS. We found that CJFS achieves better performance than vanilla ext4 with JBD2, but the resource efficiency is still worse than ext4. Note that fast commit performs better than CJFS. I'll talk about this during the evaluation. Now let's look at the design of fast commits. ext4 performs journal commits every 5 seconds by default. Additionally, when user calls fsync, ext4 performs journal commits as well. I'm calling these slow commits because these are vanilla JBD2 commits. In fast commits, what we do is that we leave the periodic journal commits as they are, the slow commits as they are, and on fsync, instead of doing slow commit, we do fast commit. As you can see, each slow commit actually commits the difference since the last slow commit. which means each slow commit invalidates all the previous fast commits. This greatly simplifies recovery process because now recovery process can skip all the fast commits and only recover slow commits and then just apply the fast commits after the last slow commit. Under some situations, fast commits may fall back to slow commits. This happens when file system tries to perform an operation which is not yet fully supported in fast commits. This actually paved a way for us to get our code upstream, because now that means this fallback path allows us to incrementally submit patches upstream so that we can add support one by one. Also, these fallbacks result in slightly increase of tail latency of fsyncs that we will see later. Okay, so now to see how FastCommit improves fsync, let's first break down fsync in ext4. JBD2 uses a dedicated kernel thread for performing journaling. When file system starts fsync processing, it first wakes up the JBD2 kernel thread. JBD2 thread, as soon as it wakes up, it first writes all the data blocks to the file system. Then it writes all the changed metadata blocks into the journal. Then it issues a cache flush command which ensures that all of these writes are written durably into the non-volatile storage of the disk. Then it writes commit marker block. This block marks the end of a journal commit, and this is written using a special command called forced unit access. This command directly skips the disk's cache and writes the write request into the disk's non-volatile storage. At this point, the commit is complete, so JBD2 wakes up the file system thread and that ends the fsync. In fast commits, we use three key techniques to make fsyncs more efficient. First is compact logging. Using this technique, FastCommit packs metadata updates in a logical fashion such that they can be expressed in a single 4 KB block. This allows us to use forced unit access commands for doing journal commits. Then inline journaling, FastCommit gets rid of the dedicated journal thread for performing fsyncs that reduces the scheduling delays. And third is selective flushing, in which FastCommit minimizes the number of cache flushes needed to during a journal commit. Let's see how all of these three together optimize the fsync path. First, let's talk about compact logging, using which FastCommit tightly packs metadata updates. Instead of recording all changed metadata blocks, FastCommit records small logical deltas in the journal. So consider the same program, which is creating a file, writing a block, and calling fsync. In FastCommit, it would result in following entries. The first is the head entry. It just marks the beginning of a commit. The second is a link entry, which is created, which records the creation of directory entry foo into the parent directory. Then add range. So now when the program called write system call, it must have, the file system has allocated a new block for this. So add range entry records that allocation. Then inode entry records the state of the inode after these modifications are done. And then a tail. Tail just marks the end of the fast commit. So as you can see, the total size of entire FastCommit transaction was just 196 bytes. The same program previously on JBD2 wrote 24 kilobytes. And since this is smaller than a single 1 4 KB block, this can be written using single IO request. Now let's see how compact logging along with other techniques optimizes the fsync path that we saw before. First, as we saw with compact logging, there is now no need to write metadata blocks into the journal. Such a block, since FastCommit is expressed as a small 4 KB block, it can be written using forced unit access command. Second, with inline journaling, since the fast commits are lightweight, they can be the commit can be performed by the same thread which is doing fsync. This reduces the scheduling delays. And third, let's see how selective flushing works. Before fast commits, JBD2 has to ensure that changed metadata written in the journal is committed to disk before completing the commit. Therefore, it had to ensure a cache flush before writing the commit marker. But now, since in fast commits, metadata updates are expressed through a single 4 KB block, cache flush is only needed if there was any data written during the fsync path. 80% of our evaluation in fsync heavy workloads, we saw that cache flush was not required. These optimizations combined together result in about 57% reduction in overall fsync latency. Let's zoom in into the latency profile of fast commits versus JBD2. While fast commit shows a great drop in mean and median latencies, at tail, fast commit latencies are higher. This is because of the fallback paths that we discussed previously. Supporting more and more fast commit scenarios in fast commits would get rid of the tail latency issue as well. Now let's look at the evaluation. This slide shows the questions that we answer in our paper with respect to fast commits. In this talk, I'll focus on the first 3 questions. First is how much reduction in fsync latency is achieved by fast commits. This is something we saw previously in the last section. Then what is the fast commits IO and byte overhead compared to other file systems? What are the performance improvements achieved by fast commits? Our evaluation was based on Google Cloud. We used GCE local SSD as the backing disk. We evaluate 4 file systems against 4 workloads. The first file system we evaluate is the ext4, which is the baseline vanilla, which acts as the baseline for all the evaluation. CJFS, which is the state-of-the-art JBD2 optimization. XFS is the other extreme of journaling files, journaling, which uses only logical journaling, and fast commits. The first 2 workloads that we evaluate are varmel and fsmark. Both of these workloads are extremely heavy in issuing fsyncs. File server and postmark, on the other hand, don't issue any fsyncs by default, but when run on NFS converts every file system metadata modifications into an fsync call as well. So this helps us see the effect of journaling on NFS. Now let's first look at resource efficiency and a byte overhead of journaling. In this experiment, we measure the total number of bytes written by the file system to the underlying device under all situations. As you can see, fast commit results in up to 56% reduction in bytes written to the device. Next, we measure IO overhead. IO overhead along with bandwidth directly impacts the cost of provisioning in cloud-based environments. In this experiment, we measure the total number of IOs issued by the file system to the underlying device. As you can see, in almost all cases, fast commits issues the lowest number of IOs. For more experiments related to cloud provisioning costs, please refer to our paper. Now let's look at the performance of fast commits. In this experiment, we measure the end-to-end application throughput of all the benchmarks. We see that in local setups, fast commit sees a huge improvement over ext4 and CJFS. However, over NFS, the improvement is not as dramatic. The reason for that is in NFS, network latency in our setup was much higher than fsync latency, which made the network delays the bottleneck of performance bottleneck. However, with faster networks such as InfiniBand or like those found in data centers, we would expect much better improvement with NFS as well. So to conclude, we present fast commits, a hybrid approach to journaling in file systems. Fast commit improves fsync latency and thereby improve the end application performance. Majority of the FastCommit code has been merged upstream, and remaining 10% lines of code are being actively reviewed. This QR code links to one of the main file that we contributed upstream. Thanks. Any questions? Yeah.